Moments and moment generating functions. The rth moment about the origin of a random variable x is given by, so let's reduce the size. The rth moment of a random variable x about the origin is given by, so we have, the notation is new r with a prime on it. So that's basically equal to expected value of x power r. And we know that this expected value equals summation of x to the r fx if x is discrete. And it equals the integral from negative infinity to infinity, x to the r fx dx, if x is continuous. Okay. Now, we note that the first moment, so mu1 prime, would just be e to the x equals the mean of x. And let's also see what the variance is in terms of the moments. So again, the next note is that if you do nu2 prime, that will be e of x squared. So that means that variance of x, which is e of x squared minus ex whole square. So e of x squared is nu2 prime minus e of x is nu1 prime whole square. Now, moments can be, of course, obtained by this kind of integration. You can obtain any moment by either the integration or the summation, whatever the case might be. But there is another way to get moments, and that is by using moment generating functions. So the moment generating function we will denote by MGF of the random variable x of random variable x is, so it's denoted by m subscript x t. So it's basically a function of t. The subscript x only indicates that it's the moment generating function of the variable x. But the moment generating function itself is a function of t. So it's the expected value of e power tx. And again, this expected value will be either obtained through summation or integration, depending on what the case might be. So we have a theorem. Let's call it theorem 1, that the rth derivative, so mr, or we can even say n. So let's say the nth derivative of mx at 0 is equal to the nth moment generating function, where mx n 0 is the nth derivative of mxt nth derivative of mxt at t equals 0. Okay. So let's do an example. Find the MGF of binomial random variable, x. Okay, so a binomial variable is a continuous variable. So in this case, we know that solution f of x for binomial is ncx p power x and q power n minus x, or 1 minus p power n minus x. All right. So the MGF mxt, as we said, that is the expected value of e power tx. Expected value of e power tx. So for a discrete variable, so binomial, in binomial, x goes from 0, 1, 2 up to n. So mxt would be expected value of e power tx. In this case, it would be a summation, since binomial is a discrete variable. So expected value of e power tx means the summation of e power tx times fx. And the summation happens over all values of x equals 0 to n in this case. Equals x equals 0 to n e power tx, and we substitute the value of fx, which is ncx px 1 minus p power n minus x. And now the e power tx can be written as e power t whole power x. And that means that this e power t and this p can be combined. So we get x equals 0 to n. ncx, I write that first, and then I write p-e-t whole power x. So that's like p power x and e power tx. And 1 minus p and minus x. Okay. So now we know that this is the binomial expansion of PET plus Q whole power n. Okay. So we can basically find moment generating function of any binomial distribution. So homework. So this will be homework 22. So let's call this as 22.1. So find the MGF of binomial of a binomial random variable with n equals. So I used q here, but q is the same as 1 minus p. So maybe we can write it as PET plus 1 minus p whole power n. So find MGF of a binomial random variable with n equals 8 and p equals 0.3. Okay. So next, let's do another example. So find the variance of a random variable x whose moment generating function is mxt is equal to so let's call it example 2. Actually, we will need a result before being able to solve this. So find variance of a random variable x whose MGF is mxt is equal to e power t minus 1. Okay. So we will need the following theorem. Solution. Let's first use this theorem and then we'll talk about it. It is known that mx, actually we have already mentioned that theorem. So that's a theorem where we said that the nth derivative of the moment generating function equals the rth moment, is equals the nth moment. So it is known from the theorem, from the previous theorem, that say mx nth derivative at 0 equals the nth moment. So we just saw a while ago, let me open the previous screen so that you can refresh. So this was the theorem that I wrote, and we also saw that the mean is the first moment, E of x equals nu1 bar, and the variance is the second moment minus the first moment squared. And therefore, to get the variance, we know that variance is equal to E of x squared minus E of x whole squared. Okay. So E of x squared will be the second moment. Because remember, Now e of x squared, yeah, would be the second moment. And that would be mx second derivative at 0, whereas e of x will be the first moment, and that would be the first derivative of the moment generating function at 0. So let's calculate the first derivative of this moment generating function. So mx, so before calculating the first derivative at 0, we just need first derivative at t. So take the derivative of this expression. So the derivative of e power anything is e power that thing again. And then we have to time it with the derivative of the power by chain rule. So the derivative of the power is e to the t minus 1. So now I have a product of two functions. So over here I can calculate mx at 0, mx prime at 0 would be e power 0 minus 1, e power 0 minus 1, and e power 0 is 1, so this factor is 1 minus 1, so that ends up being 0. And then we need the second derivative for the second moment, mu. So first let's calculate the second derivative at t. So now we will have to use product rule on these two. So derivative of first function is e to the t minus 1, and then e to the t minus 1 by chain rule. So all this is the derivative of this, and then you keep the second one unchanged, plus, and now you keep the first one unchanged. I'm using product rule of derivatives. So now I keep the first one unchanged and time it with the derivative of the second. So the derivative of e to the t minus 1 is just e to the t. Okay, I need this mu 2 prime. That's the second derivative of the mgf at 0. So now substitute t equals 0 here. So I get e to the 0 minus 1, e to the 0 minus 1, e to the 0 minus 1, plus e to the 0 minus 1, e to the 0. And now this part is gone because e to the 0 is 1, so 1 minus 1 is 0. So we have a factor of 0 here. So this whole thing is gone. And this one would be, so 0 plus e to the 0 here is 1, so 1 minus 1, and then e to the 0 is 1. So that's just e to the 0 times 1, and that is 1. So mu 2 prime is 1. So we needed the variance of x. Variance of x equals mu 2 prime minus mu 1 prime squared. Yeah, second moment minus the first moment squared. So second moment is 1, first moment was 0. And the variance ends up being 1. So as homework, you find the variance of a random variable whose MGF is mxt equals 1 over 1 minus 3t. Okay. And now let's discuss some properties of MGF. Properties. Let's open a new screen. Properties of moment generating function. So first property is uniqueness. And that says that if x and y are random variables that have the same moment generating function, if x, y have the same MGF, then they have the same probability distribution function. Probability distributions. Or the same probability functions. Second property is that M of the translation of a random variable x plus a equals e power at mxt. So where a is any real number, third property is that M of a times x t equals mx of at. Fourth property, so again a is any real number, any. So in this case, a would be any non-zero real number, because otherwise a times x would just disappear. Any non-zero. The fourth property is that if x1, x2, so on up to xn are independent random variables, then with MGFs mx1 t, mx2 t up to mxn t, and y is the sum of all the x's, x1 plus x2 plus xn. Then the MGF of y, so myt, is the product of the MGFs of the x's. mx1t times mx2t times so on times mxnt. So the MGF of a sum equals the product of individual MGFs as long as the variables are independent. Okay. So let's do an example. So let me see if I numbered the previous homework problem. So that would be homework 22.2. So let's say X is a binomial. Random variable with n equals 3 and p equals 0.5. Y is a random variable with MGF MYT equals let's say 1/1 minus t. Then find the MGF of two x times y plus 3. Okay. Solution. So we first go use the property 2 that the MGF of x plus a will be e to the at mxt. So by property 2, m of y plus 3t equals e to the 3t myt equals e to the 3t over 1 minus t, because the MGF of at the myt is 1/1 minus t. Okay. And then we have to figure out what's the MGF of 2x. So here we use property 3. By property 3, MGF of 2x equals, so let's look at property 3. Property 3 said that m of ax is mx at. So we will have m of at. So mx of 2t. Now, for the MGF of x, we are told that x is binomial, and we've just seen the binomial. So we know that MGF of a binomial random variable is, so we had it as b of et plus 1 minus b whole power n. So in this case, so therefore mxt, b was given to be 0.5. So 0.5 e to the t plus 1 minus 0.5, and n was given to be 3. So 0.5 e to the t plus 0.5 whole power 3. So that's for mx. And if we want m of 2x t, that would be mx of 2t. So replace t by 2t here. So it'll be 0.5 e to the 2t plus 0.5 whole cube. Okay. And so we have the mx, m of 2x. And so we have the MGF of this one, and we have the MGF of this one. But now this is, so okay, actually I meant find the MGF of 2x plus y plus 3. Okay. So I found the MGF of 2x, I found the MGF of y plus 3, and then by property 4, I know that, so we should have also been told that x and y are independent. Assume x, y are independent. So then by property 4, the MGF of the sum will be equal to the product of individual MGFs. So by property 4, MGF of the whole thing, so M of 2x plus y plus 3 equals the product of the individual MGFs. For the 2x, we had 0.5 e 2t plus 0.5 cube. And for the y plus 3, we had e to the 3t over 1 plus t, 1 minus t. Okay. And now here we've used the fact, now we were told that x and y are independent, but we are using it on the 2x plus y plus 3. So if x and y are independent, then any multiples of them and any translations of them are also independent. So x, y independent implies, so note that if x and y are independent, then ax and y plus b are also independent. In fact, in general, any functions of x and y will be independent. Because any function, ax is a function of x, y plus b is a function of y. So any functions of independent variables are also independent. Okay. So let's have one more homework. So homework 22.3. The MGFs of x and y are, so mx t equals e power t plus t squared by 2, and myt is let's do 0.4 et over 1 minus 0.6 et. So find the MGF of x plus 3 plus 4y.